Hi, this is Saka, and I'm back, and I'm here to film the second half of the Unit 9 pretest. And here we go. So for 13, they ask you a measure of separation between positive and negative charges in a polar molecule is called what? And basically, the idea here is that we're looking for the difference. Basically, what it's saying is we're looking for a difference in electronegativity. And so we know that this is basically polarity, and another way to say that is dipole moment. 14, which intermolecular force is present in octane, or the strongest intermolecular force? So we have C8H10. So it's basically, we have a bunch of carbon-carbon bonds. I mean, if I want to draw it out, it would look like this. 1, 2, 3, 4, 5, 6, 7, 8. And then we would have H's all over the place, like this. And so when you're looking at this thing, you definitely know it's a covalent compound, right? So the next thing you have to ask yourself is whether or not this is a polar or nonpolar compound. So this is the way you would tell. So we have C-C bonds within this molecule, so definitely those are nonpolar because you have C connected to itself. We also have a bunch of CH bonds, and they're basically very low polarity, but for our purposes, they're essentially nonpolar. And so since everything's nonpolar, remember the only force that could act upon a nonpolar molecule is London dispersion forces only. The other ones, like vapor pressure and viscosity, are properties, and dipole moment and dipole are this. This is just polarity, and this is definitely not dipole because it's not a polar molecule. 15, the force exerted on a gas and its surroundings in equilibrium. This is just simply the definition of vapor pressure. So the idea here, guys, is if we have a closed system and we have a liquid, basically what you're going to have is you're going to have vaporization occurring, and then eventually you'll saturate this open area with gas vapor, and then eventually that gas will begin to condense back to liquid. And so when you get an equilibrium between the gas phase and either liquid, and this is also true if we had a solid and gas equilibrium, this is called the vapor pressure. Okay, you can imagine the intermolecular forces will have an effect on what the value of the vapor pressure is. And we'll get to that a little bit later if we have time, or if some of the questions come up like that. 16, which of the following is related to the ease at which individual molecules of a liquid are being able to move with respect to one another? So this is just another way to say viscosity. So the idea here is viscosity is resistance to flow. So if I have, if we looked at the different intermolecular forces, let's say we had H bonding, it would have the highest viscosity. Dipole would be second highest, and then London dispersion would have the lowest viscosity. And this will generally be true assuming that the molecules that we're looking at are relatively the same in size. It can kind of change quite a bit depending if there's big differences in the sizes of the molecules. But this is a general trend that would be true assuming the sizes of the molecules are about the same. Okay? All right, number 17 here. The y-axis, we know this. You just have to go back and look, and we know that the pressure is always on the y-axis and temperature is always on the x-axis for phase diagrams. 18, okay, this one's interesting. So which one possesses the greatest dispersion forces? Just because you have London dispersion forces doesn't mean they're all equal to each other. The degree of London dispersion forces matter, and it's a function of the total electrons that are available. Okay, and what we're talking about here is the total valence electrons. I wasn't sure if you knew that. So if we look at SiF4, we have 4 from the H's, 4 from the Si, so there are 8 electrons, 8 valence electrons if you count both the Si and the H's. For carbon, we have 4 and then 7 for each Br, so 28 plus 4 is 32 electrons. For carbon dioxide, it's 4 plus 12 So that's 16 electrons. For Cl2, that's 7 times 2, so that's 14 electrons. And then Si has 4. Each S has 6, so 12 plus 4, whoops, is 16. My earlier presentation just jumped out at me. Okay, so because this one has the greatest total valence electrons, it would have the largest London dispersion force. Because think about it. Remember, London dispersion forces are temporary dipoles. Oops. And this is due to the random movement of electrons um, within the molecule. So the more electrons you have in the valence, the greater likelihood um, you're going to have more temporary dipoles. 19. So which of these molecules pores the slowest? So if we're looking for the slowest, we're looking for the highest viscosity, and we're looking for the substance with the strongest intermolecular force. And if we're looking for the strongest intermolecular force, we're looking for something with hydrogen bonding first. Br2 is nonpolar, so it has London dispersion forces. SiO2, even though it has polar bonds, it's nonpolar, London dispersion forces. Same thing with CF4, same thing with C6H6, so pretty obviously this one was going to be water. Okay, 20. Okay, so we know that there's a difference in electronegativity between P and Cl. So the Cl, since it's more electronegative, will get the negative little thingy here. And then the phosphorus end, since it's less electronegative, will get the positive one. So that's why it was C for that one. 21, electronegativity differences. Well, electronegativity differences we can use it to explain bonding in general. So the difference in electronegativity, if it's high, it's ionic. If the difference in electronegativity is quote unquote medium, it's polar covalent. And if the change in electronegativity is low or 0, it's nonpolar covalent. So it can actually be used to explain all three of these things here. 22, of the following which are attractions are due to electric charges. Well, for this one, again, it's just saying difference in electronegativity, which results in a different charge. We're talking about permanent dipoles, and this was kind of an awkward way of saying dipole. Oh, my writing's horrendous. And we could temporary dipoles are London dispersion, and it can also be used for ionic bonds. Okay, because that's remember, a big difference in electronegativity. 23 here. Which of the following compounds exhibit a polar bond? So now it's just asking for a polar bond. It's not asking about whether it's dipole, or hydrogen bond. You're just looking for things that are polar. So you're looking for polar bonds, and so if something is polar, you have to have two things. One, you have to have polar bonds, and you have to have a lone pair of electrons around the central atom. If there's no central atom, if you have polar bonds, that's good enough, okay? So that's why A is polar, because there's a difference in electronegativity between Cl and H. SF2 also, because SF2 has a central atom, and it looks like this. Oops. Where you have two lone pairs. There are valence electrons for F, but I'm not drawing them, so that would make this one polar. This one's no good because this one's ionic, and this one is also ionic. And for this one, this is carbon monoxide, and even though there's no central atom, there is a difference in electronegativity, so that one is polar too. And then the last one, you're looking for dipole-dipole interactions. Again, you're looking for something that's polar, and you're looking for something where the H is not connected to an OF or N. So SF2, we just did SF2 before. We know this one's polar, and the interaction will be dipole-dipole. NH3, even though it's polar, its interaction is hydrogen bonds, so this one would not be a choice. This one, is nonpolar, so it's nonpolar, and so it would be London dispersion forces. This one's nonpolar also, London dispersion. NCl3 is polar, so NCl3 looks like this. Oops. And see how the center atom has this lone pair right here? That's what I mean by lone pair. So this one is, and there's no hydrogen in this, so this is dipole-dipole. NaCl is ionic. Okay, so that's why A and E are the right answers. And hopefully this helps, and good luck studying, guys. And maybe I'll be on later with another video if you guys need it. Otherwise, I'll see you tomorrow. Good luck.